Resource allocation markets. Kelly considered the following general setup for modeling resource allocation. Let R be a set of resources and C maps from R to Z plus be the function specifying the available capacity of each resource. Let R in capital R let A equal to the set A1, A2, A3 until AN be a set of agents and MI in Z plus the money available with agent AI. Each agent wants to build as many objects as possible using resources in R. An agent can be able to use several different subsets of R to make one object. Let Si1, Si2, Si3 until Siki be subset of R usable by agent AI Ki in Z+, denoted by Xij the number of objects AI makes using the subset Sij. 1 less than equals to J less than equals to Ki. Xij is not required to be integral. Let Fi equals to the summations of Xij summing with J starting from 1 to Ki be the total number of objects made by agent AI. We will say that Fi 1 less than equals to I less than equals to N is feasible if simultaneously each agent AI can make Fi objects without violating capacity constraints on R. Kelly gave the following convex program and showed that an optimal solution to it satisfies proportional fairness, i.e., if Fi star is optimal solution and Fi is any feasible solution, then the summations of Fi minus Fi star over Fi star seen with index starting from 1 to n is less than equal to 0. Intuitively, the only way of making an agent happier by 5% is to make other agents unhappy by at least a total of 5%. Maximize the summations of mi times log of fi summing for all those ai in A, subject to the constraint that fi equals to the summations of xij summing with the index j starting from 1 to ki for all ai in A. And another constraint is that the summations of xij summing for all those ij such that R is in Sij is less than equals to C of R for all little r in capital R, where the C of R is the little r. And the Xij is greater than equals to 0 for all ai in A, 1 less than equals to J less than equals to Ki. This general setup can be used to model many situations. The following are examples of situations of a combinatorial nature. 1. Market 1, flow market. Given a directed or undirected graph G equals to VE, E is the set of resources with the capacities specified. Agents are source sink pairs of nodes S1, T1, S2, T2 until SKTK with money M1, M2 through to MK respectively. Each SITI path is an object for agent SITI. 2. Market 2, given a directed graph G equals to VE, E is the set of resources with the capacities specified. Agents are A, which is a subset of V, each with a specified money. For S in A objects are branchings, rooted at S and spanning all V. 3. Market 3. Same as above, except the graph is undirected and the objects are spanning trees. Using KKT conditions, one can show that an optimal solution to this convex program is an equilibrium solution. Let PR, R in capital R, be Lagrangian variables corresponding to the second set of conditions. We will interpret these as prices of resources. By the KKT conditions, optimal solutions to Xij's and the PRs must satisfy the following equilibrium conditions. 1. Resource little r in capital R has positive price only if it is used to capacity. 2. Each agent uses only the cheapest sets to make objects. 3. The money of each agent is fully used up. Since the objective function of convex program 5.2 is strictly concave, one can see that at optimality, the vector f1, f2, f3 until fn is unique. Clearly, this also holds for every equilibrium allocation.